Lesson 4, composite functions. Some key things that we're going to talk about are discrete domain, where you graph something that has distinct points that are unconnected. Then you can have a continuous domain, which means we're dealing with connected points. Okay, let's get into some examples of that. So if I were to ask you to graph the function f of x, where f of x is the quantity of x minus 2 squared minus 1, for a domain, so this is indicating the domain, from 0 to 5, where 5 is not included and 0 is. What you want to do is set up a table of values like I have, and you're going to say, here's 0, 1, 2, 3, 4, 5. Now we're going to plug in 0 to the function, and we would get something like 0 minus 2 quantity squared minus 1, which if you evaluate that, you're going to get negative 2 squared, which is 4. 4 minus 1 is 3. So we're going to graph 0, 3. Then you're going to do that again with 1. So we have 1 minus 2 quantity squared minus 1, and that equals, well, that'd be negative 1 squared is 1. 1 minus 1 is 0. So we're at 1, 0. Let's double check that. Yeah. Then you plug in 2. 2 minus 2 squared is 0. 0 minus 1 is negative 1. Then you plug in 3. 3 minus 2 squared is going to be 1. 1 squared minus 1 is going to go back to 0. 4. 4 minus 2 squared is going to give you 2 squared, which that's 4. 4 minus 1 is 3. And then last but not least, you plug in 5. 5 minus 2 is 3 squared, which is 9. 9 minus 1 is 8. So I have to go to 5, 8, which is in my function, but that's okay. Because the domain was connected, it was a continuous domain, meaning x can be anything in between 0 all the way to 5, I would graph this. Now I want to check. 0 is definitely a solid dot because that says equal to. But then I check 5, and I see that 5 is not equal to. So I'm going to erase what I had, put an open hole, and that indicates that I went to the x value of 5, but I'm not touching 5. In this case, f of x is a continuous function over the domain 0 to 5, uninclusive at 5. Some other key things we want to mention, if you notice, if we were to talk about transformations, which was our last lesson, we would know that the a value of this transformation, the thing in front of the parentheses, is equal to 1. The b value, the number in front of the x, is also equal to 1. The h value is with the x, and it says negative 2, but it's really lying, it's positive 2. And then the k value is negative 1. These 2 points at the bottom, h and k, indicate the vertex. So I should be able to go to where x is 2, y is negative 1, and I could label that as my vertex, positive 2, negative 1. That's an important thing because that also indicates symmetrical properties. So if you notice, when I was 1x unit away from that vertex, I have the same y value on either the left or right side. If I was 2x values away from that vertex, I have the same y value on the left and right side. So that's a good helpful hint to know I did do my evaluations correctly. Okay, let's go to the next example. If I asked you to graph g of x for the square root of x minus 4 plus 5, I'm going to change the domain just real fast, and I'm going to only ask you to graph when x is 5, 6, 7, and 8. I'm doing this intentionally because sometimes you get these values that are not whole numbers. If I had done the other ones, you would have gotten perfect whole numbers, and then that's a little different. So imagine you got 5, 6, 7, and 8 as the domain that I'd like you to graph. Well, what that means is, again, we're going to evaluate those numbers. So we're going to plug in 5 to our function. So 5 minus 4 is 1. Square root of 1 is 1. 1 plus 5 makes 6. So I can graph when x is 5, y is 6. Then I plug in 6. Well, 6 minus 4 is 2, and I can't take the square root of 2, so I'm just going to write the square root of 2 plus 5. I do the same thing for 7. 7 minus 4 is 3. Again, I can't take the square root of that, so I have the square root of 3 plus 5. And then I plug in 8 and hope I can square root this, but 8 minus 4 is 4. Yes, it is square rootable. That gives me 2 plus 5, which makes 7. So that means I can graph 8, 7. Now, without using a calculator, can you graph those other 2 points? The answer is yes. You know how to approximate. You can assume that those points are in between 6 and 7. It is okay to just randomly put dots between those points for this example. Notice I'm not connecting these dots. The reason I'm not connecting these dots is because g of x is a discontinuous graph on a domain of 5, 6, 7, and 8. The only x values that I want you to graph are when x is 5, 6, 7, and 8. I don't want you to graph 5.5. I don't want you to graph 6.7. I want you to graph solely those whole numbers and leave it like that. Okay, now let's get into composite functions. So, composite functions are when you take a function, say f of x, and you input it into another function, say g of x. There's 2 ways you can write that. You could say g of f of x. Notice the parentheses, I pause and say of. But you can also write it like this, g o f of x. Notice the O stands for of. The parentheses also stand for of. So g of f of x. You can get some things that look funky like this, where it says f o f o f of x. But really you need to remember that the O is a parenthesis. So starting from the inside, these 2 first, you would say you have f of x inputted into the f function, which is inputted into the second f function. So you're plugging it in, input, input, and then you get a final output. Okay, so let's do an example. Like, how do you do this? Well, if I asked you to do f of g of 3, you would first start with g of 3 and find what g of 3 equals. So off on the side, I have this example. If f of x is equal to x squared plus 1 and g of x is equal to x minus 4, well, we're going to find g of 3 first. That's what this example says to do. If I'm being asked to find f of g of 3, my first step is to find g of 3. Step 1, what's g of 3? Well, I plug that into my g function and I get 3 minus 4, which is negative 1. Now, I now know that g of 3 is equal to negative 1. So I can come back to the original statement, which says g of 3 up here. Let me get a very different bright color. G of 3, and I can replace that with negative 1. So really, step 2, I'm doing f with an input of negative 1. So when I do that, I go to my f function, which says I take negative 1 and I square it, and then I add 1 to it. When I do that, I'm going to get 1 plus 1, which makes 2. Whoops, my brain's going too fast. And then I get f of g of 3 is equal to 2. Now let's do it with some letters. So, say for example, I had f of x equals 3 minus 4x, and then I had g of x, which equals x squared minus 3x plus 9, and I wanted to find h of x, which is f of g of x. Remember, that could also be written like this, f o g of x, and also we can use different groupings. So you might see sometimes it says f of g of x. Sometimes this is another form of grouping. All of them mean the same thing. So what I want to do is find g of x first. Well, g of x is provided for me. This is g of x. So now I can rewrite the first statement and say, really, I want to do f of x squared minus 3x plus 9. Now remember, when I say of and then I have this long trinomial, this long trinomial is my new input. So what I want to do is go to my f function and say, well, f is really 3 minus 4 times something, the x. The x is going to be replaced with that box, that trinomial. So I have 3 minus 4 times x squared minus 3x plus 9. Now I'm going to distribute and combine like terms. So my final answer is going to look something like 3 minus 4x squared plus 12x minus 36. Combine your like terms, you're left with negative 4x squared plus 12x minus 33. And you're done. That's h of x. Okay, let's do another one. So say you had f of x, which was 3 minus 2x, and g of x, which was x squared minus 4x minus 8. If you're being asked to find k of x, which is g of f of x, means we're going to take the f function, input it into the g, and then we're going to evaluate to find k. So k of x is equal to g of f of x. Remember, I already have f of x. It's this great statement in that box, so I can replace f of x with that box, meaning I can say g inputs, I'm going to input into my g function 3 minus 2x. Now, my g function is x squared minus 4x minus 8. So everything that has an arrow is going to get that 3 minus 2x in parentheses. So I have something squared minus 4 times something minus 8. That something, again, is this 3 minus 2x. So 3 minus 2x goes here, 3 minus 2x goes there, and then we evaluate. Now, we need to remember that we can't distribute that exponent, but instead, if we need, write it 2 times for your brain so that you remember you're going to double distribute here. And then from there, I'm going to distribute that negative 4 and get negative 12 plus 8x minus 8. And then from there, I'm going to double distribute on my 2 parentheses set. So I'm going to get something like 9 minus 6x minus 6 more x makes minus 12x plus 4x squared minus 20 plus 8x. And then I combine like terms, understanding that negative 20 minus 9 is going to combine. I'm left with 4x squared minus 4x minus 11. And that would be g of f of x. Okay, let's change it up a little. Let's not just do f of x as an input or g of x as an input. What if we did f of x minus 2 as an input? So using that same f function where we have 3 minus 2x, and then a g function where we have x squared minus 4x minus 8, I need to find p of x. Now p of x says that I want g inputted with f of x minus 2. Now that's a little different than we've been doing, so what I'm going to do is do some side work. I need to find what f of x minus 2 is first, meaning I'm going to go to my f function, that thing that says 3 minus 2 times something, and I'm going to write that x minus 2 as my something. Now I'm going to evaluate this. This would be 3 minus 2x plus 4. Combine your like terms, and you're sitting with 7 minus 2x. From here, now I know what f of x minus 2 is. It is 7 minus 2x. So what the question's really asking me to do is go to the g function and input 7 minus 2x for every x that appears in the g function. Okay, so now I say something squared minus 4 times something minus 8. That is the basis of my g of x function. Now I replace it with 7 minus 2x. By it, I'm talking about x. I'm replacing x with 7 minus 2x each time. And then I do some amazing math and get some great answer. So 7 minus 2x squared is really 7 minus 2x times 7 minus 2x. Then we distribute that negative 4 and get negative 28 plus 8x minus 8. From here, we're going to double distribute this step. So we have 49 minus 14x minus another 14x makes minus 28x. Then we're adding 4x squareds. And then we have minus 36 plus 8x. You can again combine like terms. You have 4x squareds minus 20x plus 13. And that would be your final answer for P of x. So what if we went into graphing land? So this is finding everything algebraically. What if we hit a graph? So my f of x is denoted by this graph. So here's f of x. F of x is all of these points connected with these lines. This is called a piecewise graph. We're going to get to that quite soon, but not yet. So this is my f of x. G of x is my table. So if we remember back from the steps, the first thing we would do is first find f of 4, meaning I look at f's function where x is 4, and I see that we're dealing with a y value of 2. That means that I can replace f of 4 with 2, and I can rewrite g. So now I have g of 2. Well, g of 2 means go to where x is 2 and find the g value, you get 1. So your final answer for g of f of 4 is 1. Okay, let's switch it up. So if you had f of g of 4, you would first start with g of 4, and you would say when x is 4, the g of x value is 2. So again, I can now replace g of 4 with 2, and I can rewrite that next statement below as f of 2. Again, that means I'm going to go to the f function where x is 2, and I'm going to find the y value that gives you, which is 0. So your final answer for f of g of 4 is 0. You might get notation again that looks like this funky one, g of 3. If you want to rewrite it, again, it's g of 3. That means we're only going to be looking at the table for this one. We're not going to look at the graph because the graph denotes f of x. So I'm going to start with the insides. G of 3, meaning when x is 3, the y value is what? Well, when x is 3, the y value is 0. So then I have that one. Once I have that, I realize that I can replace 0 with this g of 3. So I can rewrite my original statement to say g of 0. That means when x is 0, find the y value, and I go to my g function. When x is 0, the y value is 3. So g of 3 is 3. Now, last but not least, you might be asked to solve. Solve means you're going to work backwards. You might get notation that says FOG of x. Remember, that really is saying that you have f parentheses g of x is equal to 4. So in order to solve this, we have to figure out what x value in the f function gave a y value of 4. So we're really being asked this question. What x value in the f function gave a y value of 4? Well, if you go to the graph, when y is 4, you'll see the x value provided is 1, which means f of 1 is 4. Now from there, we need to realize that that 1 is actually representing g of x. Notice it's in the same box as the g of x. It's in the same space. So now I can say that g of x is equal to 1. which means, again, go to your G, the table, and I need to look where the G of X value is 1 and find the X value that produced that. That would be 2. Okay, that's the lesson. Have a great day.